Let's go. Good afternoon and welcome back to Mr. Middlebury's Maths World. This is the way it is. Sometimes logarithmic equations look more complicated than they need to be. We're going to make use of the most basic log law to say that 3 times x is equal to 18. I mean, obviously for this to be true, what's in there must equal what's in there, same base. So we just say that 3x equals 18, therefore x equals 6. Okay, so that's that one. Now, what have we got here? Alright, in this one we've got to make use of that technique we saw in an early lesson about letting messy bits equal something. Okay? We're going to use a technique called substitution to solve this. So by messy bit, what I would mean here is that we're going to replace all of our log base 10x with a pronumeral, let's call it a. So we say let log base 10x equal a. We've used this technique a couple of times before. So what we're going to do is say that therefore a squared plus just a minus 2 equals 0. And then we're going to solve for a and then substitute back in log 10x for wherever a appears. So what have we got here? We're going to use product sum number again. The product is 1 times negative 2 equals negative 2. The sum is the coefficient of the middle term, which is 1. And here, the numbers we are after, one of them's got to be negative. It's going to be 2 and 1. And the larger in magnitude must be positive. So that times that equals that. That plus that equals that. Okay, therefore, a plus 2 times a minus 1 equals 0. And the null factor theorem is telling us that either that equals 0 or that equals 0, and we just say that. Therefore, a equals negative 2 or a equals 1. Okay, now what did a equal? Well, a equaled log 10x. So we'd say log 10 x equals a equals, what I'm saying is that equals negative 2 because a, here we go again with the pen, equals that, but a equals negative 2, or, go over here maybe, a equals negative 1, positive 1, but a equals that. So log 10x equals 1. Alright, now let's see if we can make sense of this. Log, now we've got to solve. Remember, base, index, number. Okay, so therefore x, now 10 to the negative 2 you should recognise as 1 over 10 squared, so in other words 100. Alternatively, 10 to the power of 1 could equal x, 10 to the power of 1, start that again over here, 10 to the power of 1 equals x, so therefore x equals 10. So we've got two possible solutions, both of which are possible in this case because we don't have a negative appearing anywhere, so that's fine. Okay, next problem. We've got a couple here, boys. Now, we're going to use the substitution technique again, but this is a bit easier than it might look at first blush. You've got to understand that this can be written as 4 log 2x. So, 4 log 2x like so. And over here, don't confuse this. This is log base 2x all squared. In other words, log base 2x times log 2 base x. So that's slightly different. So we're going to leave that to this sort of situation here. So we're going to leave that as it is and say that we're going to let a equal, you can probably guess, log 2 base x. Log base 2 x is what I should say. And you can see, I think, from here, that now 4 times a, therefore 4a is going to equal a squared, isn't it? A squared. So let's just take the 4a to the other side. A squared minus 4a equals, well, it equals 0. Therefore, factorising in terms of a, we get a bracket a take 4 equals 0. Therefore, a equals 0, or a equals 4. Right, what did we say a was equal to? Well, we said it was equal to log base 2 x. So therefore, log base 2 x equals 0, or log base 2 x equals 4. Therefore, now can you see here, lads, 2 to the power of 0 is 1. So we can say x is equal to 1. So what we're saying is 2 to the power of 0, which is 1, is equal to x. So x is equal to 1. Put another way, remember, log base anything 1 is equal to 0. Or, just running out of room, and I don't want to take up room here, so 2 to the power of 4 equals x is what we could say here. 2 to the power of 4 is equal to x. Now 2 to the power of 4 is 16. So therefore x equals 16. Just checking to make sure that both are feasible. Yes, it seems to be quite feasible that should be the case. Okay, our fourth example isn't as tricky as it looks, I would suggest. What we're going to do here is simply divide both sides, multiply both sides by the denominator. So we're going to say log base 10x is equal to 4 lots of, taking this over here, log 10 base 10 2, isn't it? Now there's a couple of ways we could solve this, but this would have to be my preference. Let's just make use of the log law and put this 4 back into here. So we could say log base 10x is equal to log base 10, 2 to the power of 4 is 16. And you can see straight away, surely, that x must equal 16, same base, that must equal that. So therefore, x equals 16. Alright, last example I want to show you, and that will complete our work on logarithmic equations. Here you can probably imagine what's at stake. It's not as bad as it looks. I don't think anyone will say it's worse. So we can say 3 to the power of 1 is equal to what's in brackets. So 3 to the power of 1, of course, is just 3. So it's equal to x squared minus 3x minus 7. Okay, now you can probably anticipate that we've got a quadratic trinomial to solve. We're going to take 3 from both sides, and that will yield x squared minus 3x minus 10 equals 0. Product sum number technique used here. The product is 1 times negative 10 is negative 10. The sum is negative 3. It seems our numbers will have something to do with 5 and 2. That's telling us one of them is negative, the product, because a negative times a positive is a negative. That's telling us that the sum, the larger of the two in magnitude, must be the negative one. Let's just check it. That times that, yup, equals that. That plus that, yup, equals that. So therefore, x minus 5 times x plus 2 equals 0. Therefore, x equals 5 or x equals negative 2. Okay, now what happens when x is equal to negative 2? Well, we get a 4 there, minus a negative 6, so it's 4. Minus negative 6 is 10, plus 3, yep, that works out. And the 5, well, that comes to 25, minus 15, minus 7. 25 minus 15 is 10, 10 minus 7 is 3. So both of those solutions are indeed feasible. So we have two solutions here. Remember, sometimes you will not have two feasible solutions. You'll have two solutions, but one of them turns out not to be possible because it will yield a negative in there. Not so in this case. Okay, so thank you very much. That ends this discussion on logarithmic equations using unit base.